In this video, we're going to be doing this problem, and it is about enolate chemistry. We're going to be doing some reactions, creating the enolate first, and then making it react with something else. Let's see what that's about. So here we have ethyl, and then this is acetoacetate. So now, when you treat it with, in this sequence, we need to figure out compound A, what it is, compound B, compound C, and we have all the reagents. So let's get started here. When you treat this with sodium ethoxide, what you're going to make is the enolate precisely. So you're going to get one of the acidic hydrogens in between the two carbonyl groups, and we know that this is a stabilized enolate. Stabilized enolate because you know that you can do resonance here, but you could also move the electrons over the other side. So stabilized enolates are good Michael donors. And the Michael donor is a conjugated addition, which is what's happening in the next step. So now I'm going to draw the other compound. Now that I have the enolate, I'm going to have the other compound here. And this is an alpha beta unsaturated ketone, which is a Michael acceptor. Michael acceptor. And this, as we said, is a Michael donor, is a stabilized enolate donor. All right, so what's going to happen now? And I'm going to remove those resonance structures, arrows, just to give you like the mechanism of what's going on now. In the next step, you're going to have the attack of the enolate at the beta carbon. So that next step is, let me do it with this color. Here you're attacking, and here you're going to move those and those as well. So now your product after that addition is going to redraw this part. This is like the same. But now here you're creating a bond between this carbon in between the two and the beta carbon. So here is a bond. So that used to be my beta carbon. And now I have beta and alpha. And I'm going to have a double bond NO negative in a metal. So that's alpha carbon. Oh, I said alpha and drew beta. All right. Alpha, beta. So you have created a new bond between this carbon here and the beta carbon. And after you, if you acidify that, you will have, say, a proton transfer step in which you're going to make the, say, enol form here. OH, H, and that is in equilibrium with the keto form. So now you have added this 1, 2, and here you will have a dot, another group here. Okay. So that is 2 carbons. That's what we have so far. And so this will be compound A. Let's label that. And from compound A, I see here that we're treating it with sodium ethoxide again, and then we make it react with this is allyl bromide. So now what's going to happen here is another acid-base reaction. Remember that you still here have another H. You had previously 2 H's, remove one to make that enolate and then that Michael attack. So in this step, you're going to be removing, so I'm going to do that. There is slightly higher. So I'm going to have this, but you also had already added the chain, remember. So this is then going to attack. This is an SN2 attack. And your reagent is this. And now what you're going to do is in that attack, simply You're going to do your SN2. And now your product, you're going to get crowded here. I'm going to have to do it like smaller to make it fit. That. And I'll be adding another group. So I need 1 carbon and the vinyl group. So 1 carbon is that, and then this, and then that. Now I have the, this is compound B. Let's label that. So B. And I'm going to have to erase some of that so that I can complete the rest of the reaction. So let's get to do that. Now we know. First step was a Michael addition, and followed by a tautomerization step here. And we got A was the compound that we have here in the bottom. And in this step, we remove an additional acidic hydrogen, so another stabilized enolate. And now this is simply doing an SN2 over the allyl substrate. That's a primary alkyl halide. But allyls substrates are good for SN1 and SN2. In this case, with that reagent, that's going to be an SN2. And so now, it says here that we treat B with NaOH and water, and then hydrochloric acid in water. What this is doing, this is steps. This is the ester hydrolysis, but since you make a carboxylate, this is your ester. We're going to be hydrolyzing that. You're going to form a carboxylate. And with acid, we are going to protonate and get the carboxylic acid, precisely. So I'm going to combine here steps 1 and 2 into 1. So 1 and 2. And simply going to hydrolyze that and do the carboxylic acid. So it will be the following. Now this is a carboxylic acid. Remember that we did that. So this is one of the groups. 1, 2, 1, 2, and the carbonyl. All right, that's what we have. The other step says here, that little triangle is heat. So what's going to happen next is a decarboxylation step. To understand the decarboxylation step, what I'm going to do is redraw this. So rotating this so that I have the OH to the other side. Let's see how that looks. So now I'm going to have rotating that. I'm going to have OH here in the carbonyl here. I'm just rotating that part. And here you will have the same 2 groups. So in the decarboxylation step, what happens is now you're going to get this hydrogen here. Here you form a double bond and that disconnect. And as you see here, this fragment is carbon dioxide. And so after the decarboxylation, so minus carbon dioxide, let's draw the structure that results. And here you're going to have, I no longer have that. But I'm going to draw, this is gone, so I can draw this one, 1, 2. So 1, 2, and 3. That's this chain below. And what else I have? Here I have 1, 2, and that vinyl. Okay, so this is again minus that. Notice that I have a, oh, that's wrong. That was an OH. Oh, just copy that again. You did grab that O here, so you're forming, here is like an enol. And that will be in equilibrium. And that favors most of the time the keto form. So what I'm doing is now the tautomerization step. In the tautomerization step, this is going to turn out into the keto form. And now I am going to have this. And that's my final compound. That will be C. So recap here. The first step was removing one acidic hydrogen here to form a stabilized enolate. which then will do, let's do it quickly here, a nucleophilic attack, my Michael acceptor. We did that compound, and that was I erased it. So, and after A, we had removed the other acidic hydrogen and attached the other group. And this is how we got to B. So we have, this is A, but deprotonated. After you A treated with ethoxide, you get the other acidic hydrogen out, and that will be acting as nucleophile, and that is my essential reaction. That is the compound here, B. And what we did next was combining this two steps. This is the basic condition, hydrolysis of an ester, HCl to protonate, and we have this. With heat, we're going to have the decarboxylation. All I did here was rotated that bond so that we get, say, H close to the oxygen here. And that's my enol form, and that is a tautomerization step. Okay, and that's my final compound C.